All right, you can start recording. Okay, before I continue with the first function of the link layer, let us revise what we did in the yesterday's class. Is the PowerPoint visible, Ramanand? So we are discussing the link layer, and within the link layer, we understood what the purpose of link layer was. A part of link layer is available in the nodes that connect the source with the destination. When I say part of it is available, we say that switches have link layer, the routers have link layer. We took an example of transportation. We understood what link layer services are provided. First one with framing, then link access with reliable delivery, flow control, error detection and correction, and to some extent half and full defects as well. Where is link layer implemented? Link layer is implemented in network interface card, that is the adapter. Call them as Ethernet card, 802.11 when we have Wi-Fi card, chipset, and so on. We also saw that there are two ends for it. One is the network part of it, one is the host, and another is the one which interfaces with card. So when we saw that adapters as the link layer, so we say adapters are communicating. The sender encapsulates a network layer datagram and then passes on to the destination with addition of headers. Now let's go to the first one that I took was framing. Let's see if it is there. Framing. Okay. I do not see here framing, so anyhow I'll stop this share and I will I'll stop the video as well so that I can use the whiteboard without any lag. All right. Now let's start with the first function. In today's class, let's start with the first function of the data link layer. And the first function that comes across is framing. So what is basically framing? It's a fixed size datagram unit that we send across. We have a long stream of bits of zeros and ones. And how do you decide if this is my stream? Then how do you decide that within this, okay, this would be one frame, here this would be another, and then I would have another one. Okay. So I had a long stream first for those who get this delayed, long streams of zeros and ones. And then this long stream was broken into this as number one, number 2, and number 3. Okay, this is basically what we do. So link layer breaks the bit stream into discrete frames. And then what do? This frame is passed in the physical layer, and physical layer actually transmits this as zeros and ones. This is what we know as fixed sized framing. We can have variable size as well, and so on. Then once this is made, a frame is made, a checksum is computed, and the frame is sent across. Then once the receiver receives this frame, it calculates the checksum once again, and then sees based on that checksum whether there has been an error or not. How do you actually create these frames? How does DataLink create the frames? To understand this, let us see first one, how frames are created. I'll write the title of this one as breaking into frames. And among this, I have a first one here. I would write as time gaps. So what we mean by this time gaps? I would write a long bit stream here. Here, this one. And within this bit stream now, I would want that I should have time gaps. So what I will do is, I would first send this one, put some gap in between, then start the next one, put some time gap in between, then start the next one, and then start the first one. And so on. So pretty simple to understand. I had a long bit stream, and how did I break this bit stream? I inserted time gaps, which I can show here. This is insertion of time gap. This is insertion of time gap. Now, this seems okay. However, this doesn't work fine. Why? Because it's like, spaces in the text like I have done. Likewise, instead of spaces, you have a time gap. You send the first part, then second and. But the problem here is that there is no guarantee of timings. Because of no guarantee of timings, we cannot use this method. If in case the first packet that we have here gets delayed, the second one arrives, this time gap is finished. So this doesn't work well. Then we have the second one. For those who came late, we are discussing this time framing. And now we have reached breaking a stream, a packet into frames, a long the long bits of ones and zeros into frames. The first one is time gap. The second one is character count. What is basically this character count? It's like you get a parcel in which you have purchased, let's say, 10 books. And on the top of the parcel, it's written to this, and below somewhere it's written contents 10 books of this, and this. Likewise, in the character count, this field in the header would specify the number of characters in the frame. The number of characters in the okay. So likewise, if I have 1,000 ones and zeros, in the header it would be written how many characters I would have. But this is again rarely used. The reason being that there are transmission error problems, and if the header is affected by that, you cannot interpret exactly how many bits are within your packets, how many characters are there within the frame. Then we use a third method of framing. And the third method is character stuffing. And what is character stuffing? Character stuffing here means we use at the start and at the end a certain characters which denotes the start as well as the end of it. So each frame starts with ASCII character, and each frame ends with an ASCII character. For example, we have DLE STX. If this is at the start of it, it means data link escape, start of text. Likewise, DLE ETX, which means data link escape, end of text. Ramanan, the whiteboard is visible?
Yes, sir. Character
So what
stuffing.
do you see?
You are writing.
What is the last thing that you see this time?
Character stuffing.
It's still at character stuffing, okay. What is it showing now?
Yes, sir. Now it's update. Example: DLE ETX. Data link escape. End of it.
All right. Then I have the okay with it. Yeah, please scroll down. I'm I'm a bit down. Or I can do one thing, I can just declare it off then. Okay, after this I'll clear off, I won't scroll it. As of now, everybody just scroll down. I'm writing below it. There can be an issue with this DLE-STX, DLE-ETX. That is in case the DLE-STX or whatever you have used for start of signal and end of signal, if it occurs within the data, this becomes an issue. So what do you mean by if occurs within the data? Mm-hmm. Okay. Right. The drawback of the character count method is that if the destination loses synchronization, first let's see the advantage of it. If, because we don't have time gaps, we don't have count of it. So if destination if destination loses the synchronization, then destination would look for DLE STX, DLE ETX to denote where is the start, where is the end of the frame. But the problem here lies that there are possibilities in which this DLE STX and DLE ETX would occur within the data. So this can interfere within it, and that's why we here mention it, we stuff with characters. That is what we have as character stuffing. And what do we stuff here actually? The sender would send a frame wherein it would send an extra DLE just before the DLE within DLE STX that comes within the text. It's like in C programming, right? You use another escape sequence if you have to actually denote -T for tab, so that the compiler gets to know that this is not the -T, this is actually this is not the /T for tab, this is actually /T only. I mean, likewise here, if there is within the text DLE STX, what it would do is before sending this, it would mention another DLE within it. This is what we understand as escape character. There in C you would have studied this as escape sequence. Here we call it as escape character. What would the receiver do? When the receiver receives it, it would simply go to this part, and if it says DLE 2 times, it would remove this DLE. It would understand this DLE STX is not the end of frame, it is a part within the frame. Is this clear? Okay. So this is what we have this. However, there are issues with character stuffing as well, because this character stuffing is very much similar to what we have as 8-bit characters. And this creates problem in transmitting of arbitrary size characters here. And what do we do here instead of that? We go on to the next one, which we call as bit stuffing. So this was our third one. I will move to the fourth one. And the fourth one we have is bit stuffing. This method allows the data frame to contain a certain arbitrary number of bits and allows the character codes with these arbitrary number of bits per character. What I mean by that, At the end of the at the start of the frame and at the end of the frame, to denote that this is the beginning and this is the end, I use flag bytes. It's like you have a red flag at the beginning and the green flag at the end. Or let's say green flag at the beginning and red at the end. Green denotes that, okay, it's coming, and red denotes it is ending. Like we use DLE STX, but we would remove this DLE STX. Instead, we would use a flag byte, which consists of a special bit pattern. And what is this special bit pattern? It's 0, 1, 2, 3, 4, 5, 6, and 0. 6 ones and zeros at the two ends. This creates one byte, that is a flag byte. So when the sender sends the frame, it puts before the data this 0110. And then we have the data. So Viksha, what do you see this time? Still as in, what was the last thing that was displayed? You can use the microphone.
Sir, it's character stuffing.
Still at character stuffing. How about Ramanan? Oh, there's a lot of lag in this. I've already written 5-6 lines after that. Let us see what else we can do. What is the last thing that you see? Okay, fine. And Samiksha, for you also?
Yeah, sir.
Okay, fine. Let me explain then this thing again. So we were discussing bit stuffing, right? What we did in bit stuffing, we used a byte in which the pattern of 8 bits is 0, then 6 ones and 0 again. This forms a flag denoting this is the beginning, and the same bit is put at the end of the data denoting that this is the end. This is flag byte at the beginning, flag byte at the end. So whenever the data link layer has to create a frame, it puts the data in between that it got from the network layer, and at the start, at the end, it will put this spatial bit pattern. So when receiver sees it with zeros and 6 ones and then 0, it gets to know that yes, okay, this is the start of the frame. Then it removes this, considering that this is the start. So flag is removed, then takes the actual pattern. And once it reaches to a point where it sees 0 and consecutive 6 ones and then again 0, what it does, it understands that this is what we know as end of frame. Again, there can be an issue with respect to this. Let me clear the board. Now I'm clearing the board and I will scroll back up. Everybody scroll back up. So there can be a problem with bit stuffing. Can anybody tell me what problem can be with bit stuffing? Can you use microphone? Any issue with sending this stuff and the last one, flag byte? No? Exactly. Abhishek, you're right. There can be a similar data byte. Good. So a point for you, Abhishek. +1. Like we had in the character stuffing, we can have a problem here in bit stuffing as well. That in between the data, it is very much possible that the data constitutes 0, 5, 6 ones and 0 at the end as well. So this is where the name bit stuffing comes. And what would we do within this bit stuffing? So whenever the sender has to send the data, what do you see now, Ramanand? Okay, fine. So Miksha, you also say the same thing?
Yes, sir.
Okay, fine. So I have this bit pattern in which this is my end of signal, this is my start signal. Fine. Now within this, how do I do bit stuffing? In bit stuffing, if I have a stream here 0 1 1 0 0 0, at one point I had an original or let me just I'm clearing this one, I write a new one. I'll first write an old one and then I'll write a new one. Okay, so I have this as original stream that I'm supposed to send. But the problem with my original stream is that at one place I have 6 consecutive ones and zeros and 0 before it. So this, if it's sent like this, the receiver would understand that, oh, this is the end of the end of the frame. So it will stop here. But actually this is not. This is just that within a frame, it encounters this type of data. So what it does, I would have this start and end. It would automatically insert a 0 bit after it finds 5 consecutive ones. So let us see the difference here. I would use red. In this case, I have at this point 1, 2, 3, 4, 5, 6, 6 ones. So this is my start here. I have written S here, and this is the end of the frame. This is my flag for start. This is my flag for end. So what happens it when the sender sends 0 1 0 1 0 0, then it's 1 1 1 1 1. It sees that I have 5 consecutive ones. I didn't say 6, I said 5 consecutive ones. It inserts a 0. That is what I have here. I have inserted a 0. Then it continues with 1 0 1 0, whatever is the remaining. Then I have the end. So this, what I have inserted here, a 0, this is known as bit stuffing. The technique here is bit stuffing. What would happen at the receiver end? Whenever the receiver receives this bit pattern, okay, it would first take this start, it would remove the start flag, fine. Then it would start with 0 0 1 0 1 0. It removes this 0. This 0 is not here. Then it continues with 1 0 1 0 1 1 0. And at the end, and then we have the end of frame 0 1 1 1 0. Okay. It sees now consecutive 6 ones and it removes that. So you would actually get this as your data. This way, the boundary of the two frames can be determined simply by looking at the flag pattern. So the flag pattern can be what I have shown it here. And if there is occurrence of the flag in between, what it does, it would simply insert a 0 after 5 consecutive ones. The receiver, when it sees 5 consecutive ones, it removes that 0 and continues with the rest. And if the receiver sees that there is 0 and 6 continue ones and then 0, it automatically would understand this is the end of the frame. This is how it works. Any question for it? Anybody? Everybody understood? There can be a question here. What if I only have 5 consecutive ones? I do not have 6 consecutive ones. In my data, I have only 5 consecutive ones, but the flag is supposed to have 6 consecutive ones. Do I still insert a 0 here? What do you think? Yes, I would still insert a 0 here. Why? Because regardless of whether there are 6 or whether there are 5, the receiver, after seeing 5 consecutive ones, would remove a 0 after that. It's there. If I have 5 consecutive ones and a 0 within the data, the sender would automatically add a 0. So I would have 5 ones and 2 zeros then. Receiver would remove that 0. I hope you understand that part. And the last one that we have in frame layer violation. Now this is applicable to those networks in which encoding is done on the physical medium which contains some redundancy. Normally, example is Manchester coding. You have studied Manchester coding, so this is, we can use that as well. We can use combinations of, normally, a bit is a high-low pair in which there is 1. 0 bit is low-high pair. Combination of low-low, high-high, which are not used for data, can be used for framing the boundaries. This you can understand. This probably you would have studied in Manchester coding as well. using that code which is not used by data. 1 is high-low pair, 0 is low-high pair. Low-low, high-high is not used by data, so use that as a framing boundary. So this ends our first part of the lecture, that is framing. Any question? No? Then I can move on to the errors, error control. Any question? Let me go to the part of error. Error detection. So yesterday we saw the function. Okay, Ramanan, what do you see now? Okay, fine. Others as well, Mahreen, Samiksha. So next part of it, what do we have here is error. Let's move it a bit here. A function of a data link layer we saw is error control as well. What is error control? You know that when a frame is sent from the sender to the destination, there is no guarantee that the 0 sent as 0 will not be received as 1. It can change to 1. We cannot guarantee any error-free transmission. Yes, we can say that error in fiber is very low, almost negligible, and error in wireless links are high. They are high bit prone error links. High error prone links. Now, the data link layer is responsible for error detection and correction as well. Normally and commonly that we see, the common method is in which the data link layer computes some checksum, adds that checksum to the header, and sends it across. The checksum is then verified by the receiver, and if everything is fine, it is okay. There can be two types of error detection and correction mechanisms. One is error detection, in which receiver would only get to know whether there is error or not. The second one is error detection and correction, in which the receiver not only detects the error, but it knows where the error is and also corrects the error. So based on this, the first one can be the single bit error. But let us see what the PPT here denotes. The figure here says we have a datagram here that is passed on. D is the data protected by error checking, which may include the header as well. And then we have the error detection and correction bits, EDC. This is sent across the link, which is an error prone link. And at the receiver end, we have the error detection code run. I mean, the error detection, whatever you have bit parity and whatever details are therein, it will check that. I won't say code is run. It will check that, and then it will verify whether there is error or not. If all the bits in D, that is the data, is okay, then it passes on to the higher layer, the network layer. If it doesn't, then error is detected. And what it does, whether it corrects it or whether it discards it and tells the sender to send again, this can be done. This is basically how the error detection works. Like I said, in high error prone links, we need it. If we have this within, if we have this used within fiber, it is an unnecessary overhead when you know that error is almost negligible. In some cases, error detection code by itself can decide that I have an error, I discard it. Then what the sender does, sender would send it again. In some cases, error detection mechanisms works in such a way in which it detects where it is and then corrects it. So the first one, before I start with the parity one, we'll first try to understand the errors that we get. We saw impairments last time. This time, let's understand what is an error. So any unpredictable change due to interference causes error within the data. What it does, it changes the shape of the signal, the interference. And it can lead to two things. The error can lead to two things. Let me annotate on this. I have text. So I am writing something in the red here. So I can have number one as single bit error. Ramanand, can you see what I'm writing here on the slide in the red? Now what am I writing now? Oh, good. That means if I write on a PPT, it's faster. Others also saw the same thing?
Yes, sir.
Good, good, Rahim. All right, that is nice then. I think I should do this. I would annotate on a PPT. It works faster that way. And what is a single burst error here? Single burst errors by the name itself means that only one bit in the data, that the given data is having an error, whether the data is a byte, a character, a packet, whatever it is. The second one is burst error, which means two or more bits within the data unit have changed from 1 to 0 or 0 to 1. Normally what happens is burst error would occur. Why? Chances is that when interference occurs, interference has some duration. During that duration, whatever you are transmitting, chances are that they would have error. For example, if you are sending a data at the rate of 1 kbps and the noise is of 1 by 100th of a second, it can affect 10 bits. Okay. Now obviously our speeds this time are better, not just 1 kbps. The same thing. Send the same data at the rate of 1 mbps. This would have an effect on 10,000 bits at the same time. Okay. All right. Now, the first slide that it shows here is parity checking. Now, in this error correction mechanism, what we have is this is the simplest form, that is the parity checks. On the left hand side, we have 1D parity check. On the right hand side, we have 2D parity check. So what do you see now, Ramanand? Okay, fine. So I would use this as the whiteboard here. So the first one we are doing is parity check. Now I want this first to explain what is 1D parity check, then I'll use 2D parity check. There is even parity or odd parity. Let's say in even parity. In even parity scheme, the sender includes one additional bit. And how is the value chosen of this bit? The value of this bit is chosen in a way so that the total number of ones is even. So value of this bit, which is known as parity bit, is chosen such that the total number of ones is even. Likewise, if you say, okay, good, Ramadan, that's fine then. We'll use this as a board now. So this means if I'm talking about odd parity, the sender has one extra bit, which is known as the parity bit. It would choose the in such a way that the value of one of parity bit make the total number of ones as odd. Let's take an example. This is odd parity. Okay. I have this data. Okay. And then I have a parity bit. I'm using odd parity. Can somebody tell me what would be the value of this parity bit if I have odd parity? Yes?
7, 7,
Good.
1.
Good. Abhinandu, you're right. It would be 0. Sorry, Samiksha, I didn't get you. The value of parity here is 0. Why? If I count the number of ones within the data that I have sent, I have 1, 2, 3, 4, 5, 6, 7. So number of ones is already odd. So I would put 0 within the parity bit so that when the receiver receives it, it checks 1, 2, 3, 4, 5, 6, 7. Yes, I have number of ones at 7 in total. So it is odd. Now what can happen is if an error occurred while transmission of this, 1 became 0. In that case, the receiver would count it and find that 1, 2, 3, 4, 5, 6. There are 6 ones. But I am using odd parity. I got even number of ones. It denotes that error has occurred. This is how it basically works. So this is my data. This part is my data and this is parity. I'll say this is data bits and I'll say this one is parity bit. But the problem with this is burst errors. This would work fine for a single bit error. But when I said that when we send the data, it's not always that it happens like that. There are much more chances that burst errors would occur. In that case, what happens is this might not work because even after having errors in many bits, the parity may be odd still. So then what do we do here is we use in this case a 2D parity. And what is the 2D parity? See how I change it. Okay. Ramanan, what do you see now? Fine. Right. I'm back in the now looking at this, the problem we saw just now in 1D was detecting multiple errors. Let's see the two-dimensional parity that is on the right side. See here the example. So the solution here is what we know as 2D generalization of single bit parity. Now we had a stream of data bits of zeros and ones. We divide that as per rows and columns here. So we would have this stream 101000 here, then the second one, then the third one. This is one stream that we have here. This is what our data basically is. Now, this was a single stream. We divided into rows and columns. What we did, then for each row, we checked its parity. Like for this one, it's 1, 2, 3. We are using even parity. So add 1 here, total became even. This is 1, 2, 3, 4. Already at even we added 0. Then we have 1, 2, 3. We added 1. Okay. And not only this, we use for columns as well. Okay. 1, 2, it's already even. So you 0, 1, 2 already even, 1, 2, 1. So we checked, we kept a parity bit for each row and for each column as well. Now when this was transmitted, an error in transmission in which 1 became 0. Now since 1 became 0 here, which can be depicted here, receiver did 2D parity check. It checked here. This is fine. But it showed that in second row, I am having an error here. Third row, it's fine. And in the column wise also, it found out this is okay and this is okay. And it detected that, okay, I have a problem here. This is in here. And based on this, I could find exactly which bit is wrong, which bit has changed. So it can detect the bit error. Not only detect, it can locate the bit error. So not just the bit error, but also the location of where the error has actually occurred, and as well as the burst errors. Okay. And this ability in which the receiver can both detect as well as correct is known as, I will write this here in green, forward error correction. I repeat, the ability of the receiver to both detect and correct error is known as forward error correction. Any question? Wait, no? Everybody understood this? The second one, let's see. Is internet checksum that is given here. I'll clear the annotations that I had done previously. Now to understand internet checksum here, first thing you have to realize that internet checksum is done on transport layer. Why we are discussing here? Because we are taking error correction and detection all together. Otherwise, checksumming method is not something that is done by the data link layer. Link layer would use parity, link layer would use CRC, that is the next one that we have. And CRC here does not denote the campus recruitment coordinator. Ramanand, are you CRC? Okay. But here CRC denotes cyclic redundancy check. But since we are discussing this here, internet error checking, so we take internet checksum here as well. Now you might have typically used internet checksum wherein you download something and the site where you have downloaded gives you a code as well. You use a simple application which is on Windows or your any Linux-based system in which you compute the checksum of what you have downloaded. Then you compare what you got from the site and the checksum which you computed from what you had downloaded. If both are same, you say there is no error within it. If there is a problem within it, then you say, oh, your data has some error. So what do we have here? We have, let's say, D bits of data, which is treated as a sequence of k integers. Checksumming sums these integers, and using this we have an error detection bit. Like it's given here, the goal is to detect errors, example flight bits in transmitted packets. Treatment of segment content as sequence of 16-bit integers. Checksum, addition, that is one's complement sum of segment content. Then puts this checksum value into UDP checksum field. What is UDP? We'll come to that. It's the transport layer's header field. The receiver computes the checksum of received segment. Again, if there is the same value, no error detected. If there is a problem, then we have an error. So this is what we have internet checksum. Bytes of data are treated as 16-bit integers. And what do you do with them? You sum them. One's complement of this sum forms internet checksum. Where do you keep this one's complement? You keep it in the header. Then you send the frame across. The receiver receives it. The receiver checks the header and gets one checksum. The receiver checks the checksum of the data by taking one's complement of the sum of the received data, including the checksum as well. Why? Because within the checksum also an error can occur. It checks whether the result is all 1 bits, and if any bit is 0, error has occurred. This is good because it relatively requires little packet overhead. For this understanding this internet checksum and CRC, I will provide you a link within the class that might help you. probably a video. And like I said, checksum in UDP and TCP, that is the transport layer, would be only 16 bits. Another comparison between the parity and CRC, that is of the link layer, with this internet checksum, what we are discussing is that, yes, this is transport layer, other two are link layer, but transport layer checksum is implemented in software within the node. Whereas the parity, the CRC that we have in link layer are implemented in the hardware, that is the adapter or NIC. Okay. The next thing that we have is cyclic redundancy check. And after this cyclic redundancy check, we'll take a bit about, block coding and having distance, which probably you might have studied, but still we'll take a bit of it to understand redundancy in coding. And after CRC, we'll be done with the type of errors. Then we'll take multiple access protocols. Okay. I'll stop here. This would be our today's class. But before we leave, I would like to know what is the status of the installation. Have everybody have installed? Problems or downloading problems? Well, yeah, I understand because of 2G. Yes, I do understand that. We'll try to see what we can do. Yes, Linux system, Rahul, I saw. Problem is that the Linux one is paid. You would need a virtual box. You would have to install Windows parallelly on it. Marin, I understand your issue. Marin, where do you live? I managed to get myself, but I understand this time it's Samiksha. You also have a problem. Where do you live, Samiksha? Jammu. Yes, I understand. 2G problem. What we can do as of now then, I mean, there is a PPT, there is an explanation. You can try to see if our second lab would be helpful or not by just seeing the demo. I understand, Marin. I understand. The speed is very less. I understand. Let's try to see one of the labs. If you think it's getting helpful, then we'll continue. If you, I mean, it's not helpful to you by this, then we'll have to find some alternative. We'll give it, we'll give one of the labs a try. If you just, but actually lab is, doing something on your own. Let me give a demo and then we'll see. Okay. All right then. I'll give some task hopefully this weekend and let's see. I'll see you in the next class. Bye-bye.